is that we have the potential for a chiral atom, okay, or a chiral center in our amino acids, which means there are two possible structures. The relationship between those two structures is that they are enantiomers. Okay. And one of the things we have to watch out for is you notice that I'm saying we have the potential for a chiral atom. Okay. What if that R group, whoops, that's not an eraser that I wanted, is an H? Do we have a chiral atom? Okay. For it to be chiral, we have to have 4 distinguishable groups. If we add that implied hydrogen, do we have 4 distinguishable groups? Is there a difference between hydrogen and hydrogen? No. So there's no chiral atom if the R group happened to be an H. Okay. That's really our only circumstance where we have to worry about it, and that only happens for one amino acid, and I always get this one confused, conveniently enough, with another A and G reference, alanine and glycine. Is it glycine? Okay. So glycine's R group is an H, which means it has no chiral atom. Every other element, or every other amino acid, has a chiral atom, which then means there are 2 possible forms for that amino acid. Okay. The nomenclature we use for it in biochemistry is in reference to their relative arrangement of the highest priority functional group, okay, when looking at the Fisher projection. Your Fisher projection takes the highest priority carbon, which 9 times out of 10, and it actually might be 20 times out of 20, is the carboxyl group of your amino acid. In fact, it is 20 times out of 20. Okay, so that atom must, or that carbon must be at the top of our Fisher projection. We will then arrange the carbon skeleton, the carbon chain, vertically straight down. Okay? And we're going to arrange it in such a fashion that every single one of those bonds is oriented away from the viewer. Okay? If you tried to build a model of this with a significantly lengthed chain, what you would notice is that the chain will spiral back on itself. It's the only way you can get this orientation. It's not easy to see, and it's not that big of a deal to stress about. Okay? But that's kind of the viewpoint that you're looking at. That then says the substituents on each of those carbons are then aimed at you. You evaluate those substituents and you evaluate for priority. Priority is based on, this is yet again something I always get backwards, atomic mass or atomic number.
Yeah, nitrogen then doesn't have our first priority if that's got the highest atomic mass.
Our highest priority, our vertical axis, is our carbon chain. Nitrogen is not part of the carbon chain. So it's our highest priority carbon goes up top. Okay. We then compare nitrogen to hydrogen. Okay. Where is the higher priority between nitrogen and hydrogen? Nitrogen. Regardless of whether it's atomic number or atomic mass, nitrogen is higher than hydrogen. Atomic number, it's 7 versus 1, or mass, 14 versus 1. Okay. Why do I never remember that? It's different in like 2 cases on the periodic table. Okay. So it is again an arbitrary stamp. Someone said, this is how we evaluate. Atomic mass or atomic number, this is how you do it. Okay. In the sake of this class, we will never encounter that exception, so don't worry about it. As long as you remember one of those, you'll get it correct. Nitrogen is higher priority than our hydrogen. We now decide where is the nitrogen located relative to the chain. The chain is here, the nitrogen is to the left of the chain, which then means this is the L form of the amino acid. If we look at the other structure, where's our nitrogen relative to the chain? On the right side, this becomes the D form. Okay. Why not use R? As you remember, organic, that confuses with R and S, which is an entirely different system. Okay, so you have to be careful within your references. The next thing to watch out for, you'll notice that I used capital letters. Why not lowercase letters? Lowercase letters are an entirely different system. Okay? Capital L and capital D come back to referencing the chirality with respect to your Fisher projection. Okay? And it will rear its head again when we look at carbohydrates. Okay? So avoid references to R, S, plus, minus, or D and L. Okay? Because those are all slightly different systems, and we want to kind of avoid that thought process. So that is our basic structure of our amino acids. Questions about that? This I personally find absolutely irritating. What is the difference between what I've got drawn here in the upper right hand, that's left-hand corner? So if we reiterate what you just said, is that there is a bond between carbon and nitrogen.
Yeah.
Both of them show a bond between carbon and nitrogen. So what is the difference? Is there a difference?
Just, I don't know how to say it, but I mean, one's I guess they're flipped in a sense.
Depending on who you talk to, there is a significant difference in what these arrows mean. With that dashed line getting bigger as it goes back, what we're saying is that this nitrogen is behind the carbon. If we look at the other one, where's the dashed line? It starts at the nitrogen, which then says the carbon is behind the nitrogen. Are those two different relationships? Those are significantly different. Okay? The textbook uses them interchangeably. It's bad mojo. They shouldn't be doing that. Okay? Some faculty get really nitpicky on that detail, some don't. I don't care. Okay? I look at it, if you're putting that dash in, I'm pretty much saying you're referencing one is behind, and I will hope that your structure is simple enough that you would then put, say, a wedge over here. Okay? I now know that that dash is referencing going away relative to the carbon because you've put a wedge on the carbon. Kind of makes sense? You'll notice also that when I hand draw these, are my dashes getting larger or smaller? They are staying exactly the same. Why? Because this other system of larger or smaller can be easily confused. So when I hand draw it, I try to avoid that system altogether, and they're all the same size. Okay, kind of makes sense? So in case you see that show up, be aware that that can be a differentiation.
Sorry, what is the one on the left versus the right mean?
So the one on the left is saying the nitrogen is behind the plane of the board.
Okay.
The one on the right is saying the carbon is behind the plane of the board.
And that's because
Because of the shape of that, yeah,
towards the one that's behind.
yeah. Okay. Really easy to get confused. And like I said, I've encountered faculty that are really nitpicky on it, and it's exceedingly frustrating. Okay, so just kind of watch out for that. So, that R group could theoretically be anything we wanted it to be. Okay, within biology, it turns out it only comes down to 20 different things, or mostly 20 different things. There's a few other less common amino acids where those R groups can become other functional groups. Because if we change that R group, we're now change the reactivity of the molecule, we want to come up with a name for it. Okay? So we've come up with some kind of representative names for each of those functional groups. If we went through and referenced them by the name every single time we looked at it, particularly for, say, a protein that let's say had several 100,000 amino acids, we don't want to go through and say isoleucine, histidine, glycine, isoleucine, valine. That would be a really long thing to write out. So we want to shorten that down. So it can get shortened down to a 3-letter code or a 1-letter code. Okay, so these are all letters. So in the case of isoleucine, that's a capital I, not a 1. Okay. You officially are responsible for knowing these. So that if you saw a sequence of letters, you would be able to say, oh, that's proline connected to isoleucine connected to tryptophan. Okay? So you need to be able to interpret the name, the 3-letter code, and the 1-letter code. Like I said again, already in a full biochemistry class, you're really expected to know every single one of these. Okay? I had plenty of tests where they just gave you a string of letters and you had to say what the amino acid was or what the protein was. Okay? For the sake of this class, you need to memorize 5. Okay? What 5 is kind of up to you, but we'll address here in a second that we want to be a little bit more careful with just randomly picking 5 or the first 5 in the sequence. So what I want you to know is the name, the 3-letter code, and the 1-letter code. Okay? As Mike started our class off with classifying our amino acids based off of their reactivity. Just having a list of these isn't super helpful. We want some other information. That other information that we could tag in there would be, say, how would we classify it? How would that molecule react in an individual environment? Well, is that going to be important? Well, if we had, say, since I don't have the R group shown up there, let's say we had an amino acid with an R group that looked like this. Okay, so that's a CH3, CH3, CH, and a CH2. Okay. If I had a protein that was just all of those, that's all it was, just that functional group. Okay, all connected. Can I predict anything about its reactivity or where it might be located?
Not very reactive.
Okay, not very reactive. Why?
You know,
Nonpolar bonds. So reference the type of bonding. We're looking at nonpolar covalent bonds, very little charge associated with that. Okay, so it would not be predicted to react with much. Okay, keep going with that. Would you likely find this amino acid or this protein, say, in your bloodstream? Why not? Why is that relevant? I mean, you already said it's nonpolar. Why is its polarity relevant to not finding it in our bloodstream? Our blood is largely composed of water. Would this molecule interact with water? No. Which would suggest that this protein would avoid water like crazy. So if we had this protein, we might likely find it in fatty tissue, okay, or potentially inside the cell wall, okay, where we had other fatty sections. So if we understand something about the functionality of the amino acids, we can then start to predict where we might find that protein, or even that section of protein. Okay? So we need to have some understanding or way to classify these so we can look at them. Okay? So this is going to be our activity. We're going to ignore task. I have tried my very best to make sure that when they classify their amino acids, they are classifying them based off of the tables provided in your textbook. Okay? Those tables were not nicely and neatly organized on a single slide, so I had to find a different slide for it. When we go through and look at the categories that are generally accepted, we have a nonpolar category. Okay? The nonpolar category is relevant because its interaction with water will be minimal, very little. So we could also reference that instead of being nonpolar as hydrophobic. It does not want to interact with water. Okay? The rest of these now become a little bit more challenging. And yeah, we're going to run into some differences already because I don't think your textbook uses an aromatic group. They went through and subcategorized aromatic groups. Anything with an aromatic ring in it gets its own category, which is kind of interesting because if we look at, say, phenylalanine, where else might we classify that molecule? In the nonpolar group, very easily shuttled over there. Why is it not? do aromatic rings have interesting properties that could potentially change how it interacts with its environment? Yes, which is why they tried to subcategorize that out. Okay. Polar uncharged R groups. Why might we want to look at those polar groups? Our polar groups will likely,
A little bit more reactive.
with, in particular,
Water.
water. These tend to be kind of your hydrophilic groups. Notice that they referenced uncharged. Why uncharged? Because if we go through and look at their last two categories, they came up with positively charged and negatively charged R groups. Those charges are becoming charged because of either an acceptance of a hydrogen or a loss of a hydrogen, meaning they were acidic or basic functional groups. So they are polar, very likely hydrophilic. Wow, what was that? Very likely hydrophilic, but also have some extra acid-base reactivity. Okay. Just to throw a fun curveball in this, why are these species negatively charged? But why did they lose the hydrogen?
They're strong acids. They're stronger acids.
They're strong acids, but if I'm at a pH of 1, they wouldn't be negatively charged. So classifying groups based on their charge is pretty questionable because if I change the pH, they're no longer charged. Okay. So these rules or these categories were likely defined based off of physiological pH, which was 7.4. Okay. All of the rules have their own little caveats within them. In each of the cases, they should be providing a name and a structure associated with that category. If they don't give you the structure, it then becomes very confusing as to what's happening within it. Okay? So when you're asked to categorize your amino acids like you were in the homework, open up the textbook to that page. I don't remember where it is, but it is chapter 3, and just match up the categories with that system, regardless of what you think is happening within the structure. Everybody has a slightly different interpretation. Okay? And again, we just addressed that. You all have the exact same teacher, and you came up with entirely different classification systems. And interestingly enough, none of you mentioned acid or base characteristics, okay? Which is a pretty important distinction when we look at our amino acids. Okay? Questions about that?
So you're gonna tell us the ones that you said that you're gonna let
Oh,
us choose, right?
yes.
What-
So, and thankfully I went through and erased all that information. Our nonpolar, we said, were hydrophobic. Our polar or our charged ones were hydrophilic. We had our aromatics, which were kind of hydrophobic. If I just went through and memorized all of the nonpolar ones, there are 6 in there, if I memorized 5, great. Okay, you now know everything about the nonpolar functional groups. But what if I ask a question about a polar functional group? Maybe an acidic functional group. You now have no concept. You have nothing to compare to. So what you should try and do is memorize one from each of the categories listed in your textbook. And the textbook is what I will reference when I build the exam. And I believe the textbook goes neutral, acidic, basic, nonpolar, acidic, basic, and then polar, neutral. And I think that's it. They might throw in a 5th, and I don't remember what it would be. But it's really those 4 categories. Is
Yeah,
it just
they
those
break
4?
polar into uncharged and charged. Or, wait. Never mind, they continue across 2 pages. Never mind.
Yeah, it does go off across 2 pages for sure. And I think they aren't even connected pages, which is even more frustrating. Yeah, that's
So
the
yeah,
changes.
you're right. Acidic, basic, polar, uncharged, and then non-polar,
Yeah.
hydrophilic, and polar.
Okay. So having an idea of those properties could then help us say if we wanted to look at the structure of a protein. Well, proteins are part of biochemistry. We will look at structure. So it's helpful if you have an idea of amino acids, because then you can classify and say, I would expect this amino acid to be located in this location relative to other locations because it's in a more water environment. Say, which of these amino acids would you likely find in the bloodstream? Right? Anything that's polar or acidic or basic, because all of those are hydrophilic. Right? A wrong answer would be any of the nonpolar ones. Okay? Kind of makes sense? Okay. So, as we already kind of alluded to, we've run into an issue when we look at our amino acids. We have an amino group and an acid group, which means we have some acid-base characteristics in every single amino acid. Some of them are more relevant than others. Okay? So when we look at our general form for our amino acid, we need to be aware of that acid-base characteristic, because that acid-base characteristic can affect our overall reactions. Right? So if we're going to look at our structure, we need to have some idea of the pKa of our acid and the pKa of the amino group. What is the pKa of most carboxylic acids in amino acids? For those of you being like, God, how would we know that? We talked about that last Thursday, just so you know. And our pKa for our amines? 9 and change. What I've memorized is roughly 2 and roughly 9. Okay. If you take a look at your textbook, they will list them, and you'll notice that they are pretty darn close to 2 and 9. Some vary kind of significantly outside of that, but most are kind of within that range. Okay? So that if we go through and look at what happens to our structure at different pHs, at low pH, what would we expect to happen? Okay, well, if we are at a pH of, say, 1, very, very low, we are at a pH that is more acidic than our amine functional groups, pKa, which means, should the amine be in its protonated state or deprotonated state? Protonated, which it is. It has that extra hydrogen. If we are at an extremely low pH, a pH value that is lower than the pKa of our acid functional group, should our acid functional group be in the protonated state or the deprotonated state? Protonated. And sure enough, when we look at the structure, I've got it drawn there. What happens if we now go to a stupidly high pH, say like a pH 12? Okay. We're now going to be in our deprotonated state for each of these. Well, our deprotonated state for the amine is just the NH2. With the lone pair. What's our deprotonated state for the acid? Well, COO minus. Does this make a significant change in the overall properties of the molecule? Well, at low pH, I have an overall positive charge. At a high pH, I have an overall negative charge. I'm going to see some pretty drastically different physical property results with those different charges. What happens if I drop to a pH that's somewhere in between? Say a pH of 7. Okay. The pH is neutral, but what does that mean happens to the structure?
One is protonated and one is deprotonated.
True. Which is which?
The carboxyl group is deprotonated.
Because?
Because it has a pKa of 2 and it's at pH of 7.
The pH is more basic than our pKa. We need to be in the deprotonated state. Okay. What about our amino group? Somebody else? Okay. Our amino group will still need to be protonated because even though I'm at a more neutral pH, it is still more acidic than the pKa of my functional group, which means it needs to still be protonated. What is now the overall charge of our amino acid? It's going to be neutral because we have the negative on our carboxylic acid balancing out with the positive of our nitrogen, and we have an overall neutral structure. Not to be confused with a non-charged structure. So one of the ways that we can kind of adjust the nomenclature there is instead of calling it neutral or neutral charged, is we can call it by a fancy name, which I know Jimmy should know. You may not remember, but I know Jimmy should know.
What you got on your Twitter, Ryan?
Oh, son of a...
You got
That is totally cheating. Zwitterion. Okay. A zwitterion just happens to be a molecule. That's totally... Did you remember without looking at that? No, I'm just curious.
Well, they talked about it in the book. So
Yeah.
good.
The zwitterion doesn't have to be overall neutral, okay, but it's saying that we have two charges, or two opposite charges in your molecule. Okay. It is typically referencing a neutral structure. Okay. So we now have these general things that are happening at each of these stages, okay, with all amino acids. One issue that pops up is that are there some amino acids that are also acid bases? Yup. Which means that R group will also carry a pKa. Right, so let's just run a generic case. Let's say the R group's pKa, and we'll try and do it in black so we get a different color here, is 4. At a low pH, what would I expect to happen to the R group? It should be in its protonated state. Depending on what that R group is, it might be neutral or it might be positively charged. If it was neutral, what atom is the R group?
Can I say it again?
If it is neutral, what atom does our R group have where the hydrogen is attached?
Oh, what is hydrogen attached to? Could be,
Did you say it's carboxyl?
It's an oxygen. If we have a neutral R group at low pHs, that R group is containing an oxygen.
could it be a sulfur?
Okay. No, and we'll run into an issue with our sulfurs. Our sulfurs do all sorts of screwed up chemistry. But it could theoretically be a sulfur as well. Okay. What if it was positively charged? What does that make that atom? It'll be a nitrogen. Because nitrogen in its protonated state is positively charged. What happens when we're at pH 7? Okay, we would remove the hydrogen because we are at a pH that is more basic than our functional group. There's no hydrogen attached. What happens at pH 12? Okay. If our pH is, or our pKa is 4, we're still at a more basic system. So our charge is going to, again, depend on what atom that R is. What is the acid-base atom holding on to it? Okay. In this case, we kind of belied some simplicity here. What if I was at pH 3? There's an extra acid-base reaction in here, which means if I'm looking at an amino acid with 3 acid-base reactivity sites, I need to look at 3 reactions. This chart is only showing 2. Kind of makes sense? Okay. Within all of this, what happens to the charge of your molecule? It changes. Okay. Some of our amino acids will carry characteristic charges at different pHs, which is one of the reasons they've been classified as they are. If you go through and vary the pH, you'll notice that the charge state for each of your amino acids within those groups stays constant. Why is that an important characteristic? If we want to separate our amino acids out, we can group them according to their reactivity at different pHs and how we could individually isolate them. So the group characteristics that we kind of attempted to do as individual groups and then looked at what the textbook had are largely based off of the changes to the amino acid structure at different pHs. Okay. So the groups they've categorized, when you change the pH, all change their charge relatively close to each other, and that's a better way to go through and classify it. That's not easy for you to do because you'll never be able to, on a test, change the pH and test what happened to their charge. Okay, that would be a whole lot of work on your end. But that's kind of the sort of history behind those classifications. Okay. There's our zwitterion. So, titration concerns. Here's our 3 reactions. Why do we need 3 reactions in this case?
Low, neutral, and high pH.
Right? Low, neutral, and high pH would really only need us 2 reactions. Because we could start low, neutral, and high. Why do we have that extra category? What was that, Jimmy?
There's 3 sides of reactivity.
There are 3 sites of reactivity within our molecule. We have the acid site, we have the amino site, and we have the R group site. So how are we going to decide what's going on at each of these stages? Okay. To start off with, what pH do you think we're at with this structure? You should all have a really big question with that. Let me fix the structure.
I don't know, because they're both different.
Really, really low. Everything is protonated. We're looking at an exceptionally low pH.
So you added the hydrogen. not
I had to add the hydrogen,
Okay.
yeah. It's a
That-
typo in the drawing.
Okay,
Yeah,
that makes sense.
yeah, it does. And it's going to periodically delete itself. So what happens as we increase the pH? At what pH would we guess our structure to change characteristics?
2,
Why 2?
because that was for their carboxyl group, it had the pK of
The-
2.
Carboxyl group, pKa, is 2. So as soon as I transition my pH through that 2 range, I would expect that structure to immediately start losing hydrogens. Why did you not say for the nitrogen?
That is 9.
That's a 9. Why did you not say for our R group?
You don't know. Well, it's around 4. I don't know.
Unfortunately, we can't say we don't know. You need to know those pKa's. So on top of memorizing the 3-letter code, the 1-letter code, the structure, and its general classification, you also need to memorize the pKa's, and in particular the 3rd pKa for the amino acids that have a 3rd pKa. Most of them do not have a 3rd pKa. If you did as your organic chemistry instructor theoretically told you to do, memorize the pKa for your primary functional groups, you already know the pKa for this functional group. This functional group is a phenol with a pKa of... Not quite. It's 9-ish. Because we have 2 9s, I'm going to actually switch that up. We'll make it a 10. For this case, I don't actually have it memorized. Okay. So what happens as we increase the pH? As soon as we clear a pH of 2, what would happen to our structure?
It would deprotonate for the carboxyl group.
We should have a negative, which I don't want to draw all the structure, so I'm just going to abbreviate. We would still have the positive and
Nothing else would change.
our neutral.
So-
Okay. What happens now? Continue to increase the pH. What happens when we clear a pH of
Over 9.
over 9? So like 12?
No, don't go that high yet, because we can't get there.
pH greater than 9 but less than...
10.
I didn't do that right. There it is. Less than 10. What happens?
And
Our carboxyl is still negative. What happened to our amine? Anything?
Yep. Lost the hydrogen.
It lost the hydrogen, so it is now neutral. Because the nitrogen started positive when it was protonated. So as soon as we remove that hydrogen, it's now neutral. And that's where we have to be careful. What happens to our R group?
Nothing.
Nothing.
Squiggly.
So now our molecule is overall
Neutral.
negatively charged.
Oh, because of the OH.
When's our next transition?
Greater than 10.
Our pH greater than 10, what happens? Our carboxyl is still negative. Our amine is?
Positive.
Our amine is?
Is it going to be negative 2 now? Because of the hydrogen.
Remember, we only have one. We have a protonated state and a deprotonated state. When you remove one hydrogen, you're at the deprotonated state. You do not deprotonate further.
Okay.
It would be what charge?
Positive.
This is protonated. At a pH 10, are we in the protonated state or deprotonated state?
Deprotonated.
Deprotonated, when we remove a hydrogen from NH3 plus, it becomes,
Negative. Right? Because we're losing.
you're losing a positive hydrogen. You started positive. We lose.
So we're in nature. Okay.
There it is. We're at neutral. And what happens to our other group? It would become negative. Okay. Our charge for our molecule changes all the way through this. That charge we can take advantage of to try and separate individual amino acids out of a complex mixture. Kind of makes sense? You are responsible for maintaining all of those and seeing what's going on with that. Okay? And because I don't trust all those images, yeah, I don't trust any of those images. So ignore those. Remember how I said you need to know acid-base titration curves?
Should they come?
Here it is. If we start with our fully protonated structure, okay, what happens is we add base.
Well, when we get to 2,
The pH will go up, whoops, slightly, but not much, until we hit a pH of 2, and now all of a sudden it starts to go up a little bit faster, and now it'll spike. Okay, remember, your pH of 2 is your buffer point. That is when your pH equals your pKa. Okay, that is your half equivalence. It is then going to spike at the equivalence point until what? Until we're getting kind of close to that 9 range. Remember, our buffer range is plus or minus 0.5, so we're going to be getting up to roughly probably 8-ish. And we're again going to plateau until it spikes again. The pH at that new half equivalence point will be our pKa for our base species, which will be about 9. Then what happens? Our pH spikes yet again, but a very little bit. Why only a very little bit?
because we just have to go to 10.
The 10 is the next buffer point. So we're probably not going to see much spike at all. We're going to have our third equivalence point. pH equals our pKa of roughly 10 before it just kind of levels off again. Fun little question that comes out of the homework is you will be given a titration curve and they will ask, what is the amino acid that matches this titration curve? How do you determine that? Your pKa is at that plateau. That gives you the pKa. If you only have 2 plateaus, what does that mean?
There's only 2 PKs.
There's only 2 pKas.
So then we don't.
Not necessarily nonpolar R group, but not acidic or basic. That becomes very problematic because I think there's 6 or 7 at most amino acids that are acidic or basic functionalities, which means if you only have 2 pKas, you're trying to select now among the 14 possible answers. That's why they don't give you all 20 in your little drop downs to figure out which amino acid it is. Kind of makes sense? And we have to stop there, because I'm well done.
So we'll know at a pKa 2 and a pKa 9